Hey guys. So we're going to do the first lesson of Unit 10. Unit 10 is about definite integrals. We're going to talk about how to do those and their properties today. If you are not here on Friday on the early release day, then just stay tuned. If you were here on Friday, you can skip ahead a little bit to where we left off, which is where I'm going to switch from the annotation to just doing animated parts of the slide. So you can skip ahead a bit if you've already seen the first few slides of this. If you weren't, then let's go. Okay, so far we have talked about indefinite integrals, where we had the indefinite integral of f prime of x. We figured out what that was the derivative of, and then got plus c as well because there was a constant at the end. And so our answers in Unit 9 when we were doing indefinite integrals were all functions of x, right? X was always in the answer, and plus c was always at the end. So now we're going to start looking at definite integrals, and they're called definite integrals because they have a definite answer. So the answer is going to be a number instead of having something with x in it, and that plus c, that kind of uncertain constant in the back, is going to be gone as well. So this is what a definite integral looks like, and I've color coded it a little bit too. So you're going to have numbers at the front. You'll see I've highlighted this kind of green and red, the A and the B. Those are actually going to be values, right? You're going to have, for example, maybe a 0 and a 3. So you're going to have the definite integral. We would say this is the definite integral from A to B. So those are x values of f prime of x dx equals f of b minus f of a. So we have numbers kind of in the front here with the integral sign, and now instead of just doing the antiderivative, so if you kind of compare this to what we did with the indefinite integral, we had the f prime of x turning into f of x plus c. We still have f prime of x turning into f, but now what we're going to do is we're going to get that antiderivative. So just like we were doing before, we're going to get the antiderivative, but we're going to plug in the upper limit, which b here is called the upper limit of integration. It's a number. We're going to plug in that number b, and we're going to subtract what we get when we plug in the lower limit a, right? So if this were a 3 and a 0, I would do the antiderivative. I'd plug in the 3, I'd plug in the 0, and subtract those things. And so my answer from that is going to just be a number, a value, rather than expression of x. So we don't need c anymore because we have a and b. You can kind of think of it that way. If you have a and b, and again, it won't say a and b, they will be numbers. But if those two little numbers are there, you don't need c at the end because your answer itself is going to be a constant because it's definite and we know what that constant is now. Okay, so the first few slides here, again, these are the ones that have already been worked out from Friday, so I'm just going to talk over what I've already written in, and you'll have to excuse the handwriting. I was getting used to the new boards as I was doing this, yes, on Friday morning. Okay, so the first step here, the notation is going to look a little different from what we've done in the past, but the process is still the same. We're still finding an antiderivative. That's always going to be step one with these. So focusing on my integrand for a moment, right? I've got here the definite integral 1 to 4 of 2x dx. Okay, so focusing on the integrand of 2x, I know that 2x is the derivative of x squared. So I'm still saying, okay, this is x to the first. I'm going to increase that to the second power, divide by the power, and the 2 goes away. What's new is I'm putting it in these brackets. And that is because this is a definite integral, and I'm using those brackets to say that I'm not quite finished with this, that I've evaluated my antiderivative, but that I still need to evaluate it from 1 to 4. So I'm going to be plugging those in to this x squared, and that's going to be my next step here. So you're always going to take the number on top. Again, we call that the upper limit or the upper bound. And when I say limit here, I don't mean it in the same sense as like at the beginning of the course, those kind of limits. It's just a boundary. So you can think of it as like the upper boundary. So I'm going to plug in that 4 for x. So instead of x squared, it's going to be 4 squared minus, so this part's always going to be a minus here. And then I'm going to plug in the 1, the lower boundary here. So upper number, plug in, minus lower number, plug in. Then I'm just going to simplify that and solve. There is going to be a lot of arithmetic like this in this unit again. So you're probably going to want to keep that multi-view handy as you're doing this stuff this unit. No graphing calculators this unit. We can't do that. Okay, so 4 squared is 16, 1 squared is 1, 16 minus 1 is 15. That's the answer. So that's it. So this first step, again, is always going to be very familiar. That's going to be the antiderivative, just like we were doing last unit. And then we're going to plug in the numbers, upper first, lower second, subtract. Okay. So over here in this second example, I have 3x squared minus 4 in my integrand. Okay, so 3x squared is going to go up to the third power, and I will divide out the 3. Remember, we're doing the antiderivative, so the powers are going up, so minus 4 becomes minus 4x. So I'm going to put both of those in the little brackets together, and that's going to go from 1 to 3. So the numbers from up here are going to go back here after my brackets. I'm going to plug the 3 into the whole thing first. So this will be 3 cubed minus 4 times 3. So that's all in parentheses together. Minus, then I take my lower number 1 and I plug that in. So 1 cubed minus 4 times 1. And then I just start simplifying. So 3 to the third power is 27. 4 times 3 is 12. 1 cubed is 1. 4 times 1 is 4. I'm simplifying all the stuff in the front first, what I was calling f of b earlier. So this is the f of b minus f of a. So 27 minus 12 is 15. Minus, this is a negative 3, so minus a negative becomes plus a positive. So it's 18. Again, I don't need c on this stuff. And here's why. Let me go back to this previous example for a moment. Let's say that I said my antiderivative was x squared plus c. Okay, if I had said x squared plus c, then when I plug in the 4 and the 1, I would have 4 squared plus c minus 1 squared plus c. Do you see where I'm going with this? If I have 4 squared plus c minus all of 1 squared plus c, the c minus c, right? Because there's always going to be a c up here in the front and a c in the back, and I'm going to subtract them out. So it's not so much that it isn't there, is that we understand that it will always get canceled out, so we don't have to worry about it. It's kind of the conventional way of doing these, that you just act like that's plus c never happened because you know it's going to cancel out. Also, another way you can think about it is when you get to the end, your answer is a constant. 15 is a constant, right? You're never going to have x on your answers because we're plugging stuff in for all of the x's earlier in the process. 15 is the answer here. It is a constant. I don't need a plus c. There's nothing indefinite about this. So that's part of the reason why these are called definite integrals, because I get a definite answer, 15, the end. Okay, so let's move on to look at some more examples of these. Okay, so I have the next two worked out here, and of course, as needed, pause the video if you need to, write things down, go slower. But anyway, antiderivative happens first, so 3 becomes 3x. Powers are going up, not down, so it's gaining an x. Next, it's 3x, so I'm going to plug in a 7 first, so 3 times 7. Always a minus in the middle. Then I'm going to plug in the negative 2, so 3 times negative 2. So this becomes a 21 in the front minus negative 6, so that's 27. That's it. See? Easy peasy. Next one here. Definite integral from 3 to 9 of dx. Now, something's not missing. This actually happens sometimes. If it looks like there's nothing in there, if I look at this other one for a moment, it's technically 3 times dx. So if I think in terms of that, the number that's being multiplied here times this dx is a 1. So I'm rewriting my integral first to put the 1 there to make it a little more obvious of what's about to happen, because now the antiderivative of 1, or the integral of 1, is x. So now I'm evaluating x from 3 to 9. Plug in the top number first, minus the lower number, and we get 6. Okay, more examples. Unfortunately, they can't always stay this easy, right? All right, if I have x squared in my integrand, power goes up to 3, I need to divide. Oh no, fractions. So 1/3 x cubed, evaluated from 1 to 2. I'm going to plug in that upper number first. So I've got 1/3 times 2 cubed minus 1/3 times 1 cubed. 2 cubed is 8. I can just stick that over the 3. 1 cubed is 1 over the 3. Subtract, and we get 7/3. Now, one thing that I had somebody ask me on Friday was, is this bottom number always going to be less than the top number? The answer is no. It is possible that the greater number is on the bottom and the lesser number is on top, and we're actually going to talk about that later in the video. So these are not always in that order. They are usually lesser to greater, like I would say 95% of the time at least. It's usually lesser to greater, but it kind of changes what it means if it's greater or lesser, and we're going to talk about that a little bit later. Okay, sometimes you get really lucky and that lower number is 0. So let's see why that's a good thing. If I have 1/3 x squared plus 1, and I increase my power to 3, I'm already dividing by 3, so if I divide by 3 again, this becomes 1/9, right? Because 1/3 times 1/3 is 1/9 x cubed. And again, the 1 goes up to x. Now, when I plug in the 4, okay, 4 to the 3rd power is 64. So that'll be 64/9. I plugged in the 4 for x. Oh, but look what happens. If I have a polynomial here, and I want to emphasize this magic that's about to happen only happens if this is a polynomial. Oh, 1/9 times 0 cubed. Cool, that's 0. Plus x, 0. Amazing. It's kind of nice when that happens. Obviously, if we have e or some kind of natural log expression here, or trig even, it's not necessarily just going to give you 0 in the back. So don't assume it. Do actually plug it in. Then if there's zeros, cool, minus 0 doesn't change anything. So anyway, I've got this 4 to the 3rd, so that's 64 over 9. Common denominator, multi-view, again, is helpful here, right? But 4 times 9 over 9 will be 36 over 9. And 4 plus 36 is 100. So that gives us 100 over 9. We do get fractions from these quite a bit because, kind of going back over here to this other example, just because when we're doing the power rule with antiderivatives, we have to divide by that power, and sometimes that gives us fractions. Even if there weren't originally fractions in the integrand, we very often get fractions in our antiderivatives. So that happens. But you have the multi-view calculator, right? So it's okay. Okay. These are a couple you tries on the next slide here. If you want to pause the video and try it on your own, you can do that. Or I'll keep talking. All right, so -2 is going to go up to -2x. -3 to 4, plug in the 4. This gives us a -8 in the front. Minus -2 times -3. Got to be careful with all these negative signs. We got a plenty of them here. So -2, -3 gives us a +6 in the back, but then we're still subtracting it because it's always f of b minus f of a. So then that gives us -14. The other one here, this is one of those things, just like with all the other power rule stuff we've done in the past, you want to rewrite it first before you try to do the power rule here. So if I have a root x, I'm going to first rewrite that. So this becomes a 3 x to the 1/2, evaluating from 1 to 4 dx. So again, I have not done the power rule yet. So all the other notation stuff, the integral sign, the 1 to 4, and the dx, none of that has moved. All I've done on that first step is rewrite it. Okay, I did a little algebra, so nothing has changed. The step where I ask myself, what was this a derivative of? Or in the case of the power rule, the step where I add 1 to the power and then divide, that is where we switch to the brackets. The integral sign goes away, the dx goes away, and we do not need plus c. So the 3 is still here. 1/2 plus 2/2 is 3/2. So I'm multiplying by the reciprocal. Now, with these, if you have to rewrite in this first step, you're probably going to want to rewrite your antiderivative before you plug in. So all the antiderivatives we were doing last unit, we weren't plugging in any numbers, right? And so we could just leave it. Okay, cool. Is it x to the 3/2 power? And we're done here. But when we're actually going to plug a 4 into that, it's kind of tricky to ask yourself, well, what's 4 raised to the 3/2 power? So we want to rewrite it before we go plugging stuff in. So up in the front, if I have 3 times 2/3, 3's cancel and it's a 2. Okay, great. X to the 3/2 power. Remember the denominator is the type of root, and it's always going to go back to the same type of root it was in the beginning, right? So it's just a root x, but then the 3 becomes a third power. Now you can write that third power in the root or outside of it. I like to write it just to the outside of it here. And the reason that I personally like to do it that way is because I know that when I plug this 4 in, for example, it's going to be easier to take the root 4 before I cube it. Okay, so when I plug in the 4, root 4 is 2, then 2 cubed is 8. Okay, so it's easier, in other words, to make it smaller with the root before you then make it bigger with the power. Okay, so 2 times root 4 cubed minus, plugging in the 1 back here, 2 times root 1 cubed. Okay, 1 is easy, right? Square root of 1 is 1. 1 to the third power, also 1. 1 times 2 is 2. Great. So in the front, I have 2 times 8 minus 2 in the back. So 16 minus 2 is 14. Okay, so picking up where we left off on Friday now. So this is the definite integral from 1 to 3 of negative 3x squared plus 4x minus 3 dx. Okay, so as before, my first step, now lovely animations, is to evaluate the antiderivative. Okay, so negative 3x squared becomes x cubed. I'm going to divide out the 3. 4x is going to become x squared, so if I divide by the 2, that's 2x squared. Minus 3 becomes minus 3x. So then we're evaluating that from 3 to 1, so we're putting it in the little square brackets. Then, remember you're taking that upper number, so we're going to take that 3 and plug it in to all of those x's, right? So negative 3 cubed plus 2 times 3 squared minus 3 times 3. All of those get grouped in a set of parentheses together. Minus, then I take the 1 and I plug it in for all of those x's. Okay, so then I just start simplifying. Okay, so I've got in the front, there's a negative 27 plus 2 times 9 minus 9. In the back, again, all still in its own set of parentheses because whatever number I get from plugging in the 1 in the back, I need to subtract whatever that number is. So I'll have a negative 1 plus 2 minus 3. Keep simplifying. Okay, so in the back, negative 1 plus 2 is positive 1. Minus 3 is going to give you negative 2. In the front, we keep simplifying. We get negative 18 minus negative 2. So that just gives us negative 16. So remember that with all of these, your solution is going to be a value. And again, we don't need the plus c when we do that antiderivative step at the beginning, because if I had a plus c, so let me switch my colors here, right? If I had a plus c kind of here, it's difficult to write with my fingers, here and here, right? If I had c minus c, it would cancel out every time anyway. So it's really not necessary to write those in. Okay, so pause the video for a moment and try these two, just like we were doing in the slides before. Do the antiderivative, then you're going to plug in the upper number, put a minus, and then put the lower number in parentheses when you plug it into the whole thing. Okay, so I'm just going to show the whole answer at once. I'm not going to go through step by step on these because this is a U try. So for the first one, should get 5. Antiderivative is x cubed minus 2x. Plug in the 2, so 2 cubed minus 2 times 2. Plug in the 1, so 1 cubed minus 2 times 1. And subtract, and it's a double negative, so it becomes a 5. Now the second of the U tries here is kind of like that 3 root x that we saw on Friday. So if I have an x squared in the denominator, I absolutely have to rewrite this first. So I'm going to rewrite that with a negative exponent, right? So I'm going to say, okay, this is x to the negative second. I'm still in the integral when I do that because I haven't done calculus yet, right? I haven't asked myself what is it the derivative of yet. So it's still x to the negative second there. When I do the power rule and increase the power up to -1, and I divide by the negative, that is where I switch to the brackets. Okay, so from -1 to 2, and then just like with the root before, if this is the kind of thing with a negative power or a fraction in the power and I kind of need to rewrite it, I want to rewrite it first before I try and plug in the numbers. So I have a -1 power, so that means that x needs to go back to the denominator. And what that means is it may look a little different when we plug those things in, right? If I plug a 2 into that, I get a -1/2. If I plug in a -1 to -1 over -1, those two negatives cancel out. However, I still have the minus in between them both. So -1/2 minus 1 is going to simplify to be -3/2. Okay, so now we're going to talk. Okay, so now we're going to kind of go through some what if scenarios. So what happens if B is less than A? So in other words, what happens if your lower limit is greater than your upper limit, right? They're backwards. Okay, so we're going to do the same antiderivative with the same limits, but in opposite order and see what comes out of it. So for the first one here, I do my antiderivative. So that's going to come out to be 1/2 x squared plus 2x from 0 to 3. So then I'm going to plug in the 3, the upper limit, minus the lower limit, which this is a polynomial. So again, that's just going to give me a 0. Okay, so if I plug in the 3, I've got 1/2 times 3 squared plus 2 times 3. Okay, so that's going to be 9/2 plus 6, which is -0. Common denominator, multi-view calculator, and we get 21/2. Okay, so over here on the right, I'm going to do that same antiderivative, right? But now my limits, my upper and lower boundaries have been reversed. So if I'm going from 3 to 0 now, watch what happens. If I plug in the 0 on top, I get the 0 now, minus, right, because I always take whatever number is on top, right? The 0 was on top, so that's what I was plugging in first, minus plugging in the 3. Okay, so I'm going to have 0 minus all that stuff from the back. There's that 9/2 plus 6 again. So this comes out to be 0 minus 21/2, which is -21/2. So if we take those two solutions and compare them, we've got positive 21/2 and negative 21/2. Now, not that this is a solid mathematical proof, but it illustrates my point. My point is that if you switch the order of your two little limits a and b, it is effectively the same thing as just changing the sign in front of the integral. Okay, so if I switch the order, it's going to change the sign on my answer, right? So that's where this negative came from in the second version, because it was kind of backwards, quote unquote. So putting the switching the order, if the lower limit is greater than the upper limit, it comes out with the opposite signed outcome from what you would have had if they were in order. Okay, here's another what if. What if they're the same number? Okay, well, let's just do a couple of these and see what happens. So first I have the definite integral from 3 to 3 of 2 dx. So my antiderivative would just be 2x. Then I'm going to plug in my f of b minus f of a. So if I plug in the 3, so I get 2 times 3 minus, plug in my lower limit. Oh, look, that's also 2 times 3 because they were both 3. Okay, well, that's just 6 minus 6, so it's 0. Okay, let's try another one, see if that happens again. So integral from 2 to 2 of 4x squared minus 7. So that would become 4/3 x cubed minus 7x from 2 to 2. Okay, see where this is going? I take the upper 2 and plug it in. Is it a gross fraction? Yes. Does it matter? No, because I get that same gross fraction in the front as I do in the back, right? Go through, simplify it, whatever. It still comes out to give me 0. They're both going to give me 0. That will always happen if your upper and lower limits are the same, right? So this integral was from 2 to 2. The first one over here was from 3 to 3. So in conclusion, this is another property of definite integrals. If the upper and lower limits are both the same number, right, whether it's 2 to 2 or 3 to 3, 0 to 0, negative pi to negative pi, whatever they are, if they are the same, then that integral is always going to equal 0 because f of b and f of a are going to be the same thing regardless of what your antiderivative is. So that can come in handy, right? If ever we happen to catch one of these where, both of these numbers are, both of these numbers on the integral are the same, we can just take a shortcut and immediately say, okay, I know that that is 0. Great handwriting on this tablet, but you get what I'm trying to say. Equals 0. That's it. Just right away. 0 every time. Only if those two numbers are the same. Okay. One last what if. This one's a little tricky. And we're going to look at what happens with these 3 definite integrals put together. These are all the same antiderivative, right? In the integrand, they're all just 2x plus 7. The first one I have going from 0 to 2. Now those are x numbers, right? So if we think about, on a number line, we think about on the number line, right? I've got a 0 to 2, and then I've got from 2 to 3, right? 0 and 2 and 3, and aren't you glad I'm not handwriting this on my tablet? Okay, so I've got a 0 to 2 piece over here on the left, then I'm going to do the 2 to 3 piece, then I'm going to see what happens when I have 0 to 3 all together on the number line. Okay. So on the first one here, I do my antiderivative. That's going to be just x squared minus 7x, evaluated from 0 to 2. Then I'm going to plug in the top number minus plug in the bottom number. So 2 squared plus 7 times 2 minus 0. So that's 4 plus 14. So that's 18. Not a 0 or anything weird like that this time. Okay. Now we're going to look at the one in the middle. So this one goes from that 2, kind of where this other one left off, to 3. Antiderivative, still x squared plus 7x because my integrand has not changed. But now I'm going to plug in the 3 and the 2. Okay. Plug in the 3, so 3 squared plus 7 times 3. All of that minus, plug in the 2, so 2 squared plus 7 times 2. Okay, so in the front, that's going to be 9 plus 21. In the back, 4 plus 14. Notice the 4 and 14 are back from before. So that gives me 30 minus 18. There's the 18 again from before. And that gives us 12. Okay. So I've got an 18 from the first one, 12 from the second one. Now, if this is x equals 0 to x equals 2, and then I went from x equals 2 to x equals 3, this last one, I'm going to go all the way from that starting value of 0 to the very last value of 3. So watch what happens with my answer. Maybe try and guess what I'm about to get for this answer. Or if you have no idea, let's just go. All right, so antiderivative, same thing, different numbers. I'm doing the 0 to 3 this time. So if I plug in the 3, 3 squared plus 7 times 3, kind of like before. But now I'm plugging in the 0 for the bottom number, so that's just 0. Cool, gotta love polynomials. There's the 9 plus 21 again, minus 0. That just gives me 30. Okay, so look at these four numbers together, right? I've got an 18 and a 12 and a 30. Well, 18 plus 12 is 30. So what happened? Well, again, if we think back to the number line, right? If I've got from 0 to 2, that's a 2, guys. Didn't you know that? That's what 2 looks like. And then from 2 to 3, okay, what did I just do? Well, I'm not going to get into the graphical implications of what an integral is in this video, but basically I did an integral from 0 to 2, then I did another integral from 2 to 3, or I could have just gone all the way from 0 to 3. And that's what the last one was doing, right? Rather than stopping kind of part way at the 2 and doing 0 to 2 and then 2 to 3, you can just go all the way from 0 to 3 and you get the same outcome. So what does that mean for us? That is another property of definite integrals. So the way that it's written here, you know algebra and what we do with letters, right? We've got the integral from a to b of f plus the integral from b to c of f. And the idea is that if I have a to b and b to c, that I can just add those together, basically cut out the middleman b value, just like the 2 up here got cut out, right? I had one that kind of ended at 2 and another that began at 2. So it's like we're saying, well, if I have that number in the middle and it's the upper limit on one of them and the lower limit on the other, that I can just kind of cut that out and just go straight from, in this case, 0 to 3, right? Any values in the middle, you could just skip over those. That is only if the integrand is exactly the same, right? So if I went 0 to 2 of f and 2 to 3 of f, then I could just combine them and still have f in there, right? These were all 2x plus 7. That's obviously very important. Okay, so last one. Another property of definite integrals is that if you have terms being added and subtracted in your integral within your integrand, that you can split them up, right? So if I have the definite integral from a to b of f plus or minus g, only plus or minus, then I can split it up into the integral of f plus or minus, whichever one it was originally, the integral from a to b of g. So what that actually looks like in practice is down here where it says, for example. So if I have the integral from 0 to 3 of 3x squared minus x, I can have one of those integrals with 3x squared dx minus, because it was originally a minus, the integral from 0 to 3 of x. So they both still are the integral from 0 to 3. and they both still have the dx in the back. Okay, so that's just a property. It's basically just saying like, look, you're allowed to split these up, right? You can split them up with whatever plus or minus was originally there in the beginning. Obviously, that is not true for multiplication or division, right? Multiplication, we've got things like the product rule, right? Calculus doesn't play as nicely with multiplication and division. That's not going to come up, but just like what we did with indefinite intervals in the past with division, right? You kind of have to work around it. You either have to do u sub, which we'll talk about later this week, but you have to do u sub or turn it into a negative exponent, depending on how it is, right? So this rule is only for addition and subtraction. One more, which is that constant coefficients or scalars can be brought outside. Sometimes that's helpful. So any constant little coefficient, so for example here, if I have 4x in my integrand, I am allowed to take the 4 out. I am not allowed to take the x out. That would kind of break the whole thing. But constant, like a 4 or a pi or whatever, you know, a 1/2, those can all be taken out in front of the integral, but then you're going to evaluate the rest of the integrand like normal. Okay, so that's it. Thank you for actually watching. This will help you be less confused later, and hopefully I will be back tomorrow. So you can work on classwork 1 in the classwork packet, and hopefully I'll see you tomorrow.